Hi and good evening, ev- everyone. I would like to welcome you on your first workshop for TezAsia Hackathon 2022. And I would like to kick off for the session with Hanchu here. Hanchu here will actually be going through this workshop called for blockchain, understanding the money revolution, and in this way, we it's like it's more towards like introduction course, or what is the blockchain about and what can you get, or understand how it evolves for money, and the aspects of how the new how this new for the blockchain revolution is all about. Yeah, so without further ado, I would like to ask Hanshu to take it from here. So thank you, Hanshu. Yeah.
Thank you, Brian. So yeah, just to confirm with the participants, like, is my screen visible? Maybe if it's visible, just write yes in the comments. And Brian, maybe you can give the confirmation. Are we
So
good?
yes, yeah.
Awesome. So today in this workshop, we will be going through the complete package of blockchain and how it's providing us a completely different version of money. So first we'll go about and understand the need of blockchain. Why do we actually need this tech? And then we'll completely break it down and understand what's inside it and how do we actually interact with it from the outside world. And next, I'll give a brief touch upon smart contracts and programmable money. Most of the discussion on smart contracts will be in tomorrow's workshop when we actually write smart contracts. And today it's mostly going to be a theoretical top level view of blockchain and both smart contracts. So before we get started, I would really recommend you guys to please bookmark this link. On this link, I have set up a table where you can find the resources for the 4 workshops that I will be giving. I have pasted this link for the slides that I will be presenting today. And apart from that, I have some reading material here, which I will be guiding you throughout the presentation. So Brian, maybe you can paste the link in the YouTube chat.
Yep. So you guys can see the link and just access the link. I have pasted like the link on the chat itself. Yeah.
Mhm. I'll also put the link for the YouTube recording after the session is over.
Yeah. Sure.
Awesome. So today the main focus for us would be how actually money works, because right now blockchains have been, portrayed to be something like of a storage solution, and also things like private identity have been the jargonish words out there. But at the base, blockchain is all about giving us a new system of money. And the best way we could understand how blockchain works is to compare traditional and fiat currencies with cryptocurrencies, which are the currencies built on top of the blockchains. So to start, let's look right from the base how physical money or paper currency works. Well, this is pretty obvious. So let's say we have Alice and we have Bob, and Alice wants to give $10 to Bob. Then she can just pick out a note of $10 and give it to Bob, right? But if she wants to give $20 to Bob, then obviously she needs to take out another dollar, another note of $10, and then give it to Bob, right? The point here is you can't double spend physical money or paper currency, right? Pretty obvious stuff. You deal with it in an everyday life. Now, in the past decade or so, we have started making transactions online, that is, digital transactions. And in the case of digital transactions, your transactions are routed through the bank servers. It's all digital, right? So in this case, the bank servers have something called a digital ledger. So let's say we have Alice and Bob, and in the digital world, your bank balance or the amount of money that you have in your account is nothing more than just a variable in the bank servers, right? So let's say Alice is paying $10 to Bob, then ideally it's going to be Alice minus 10 and Bob plus 10, right? And it's definitely shouldn't going to be this, because if Alice is spending $10 but Bob is getting 20, then that is called double spending, right? So the software is faulty. So long story short, in the digital world, the bank's software is preventing double spending. Now I'm focusing so much on double spending because double spending is the concept around which the whole system of blockchain is actually designed. So now you would ask, like, what exactly is the problem here? Like, you have been making digital transactions every day. Like, just now you might have used Paytm. You don't really see a problem in this whole process of digital transactions. Well, the point is the problem is not in the process of the transaction. Rather, the problem is that the banks own your money. For some reason, I'm not getting the, yeah, okay, the pictures are here. So the banks own your money. When you're depositing your money in the bank has complete control over how they use that money. So usually you end up getting some interest on your savings account or on your fixed deposits, and you're able to get that because the banks further invest your money in in some kind of an investment entity. Now, usually there are all kinds of regulations that the banks can't make risky investments, but as we have seen with the 2008 financial crisis, when the banks in the US ended up making a whole lot of risky investments in the housing market, and they ended up losing a whole lot of money, and the whole global financial system collapsed for almost a decade. And then the 2018 PNB scam in India, where Punjab National Bank ended up making bad loans of about $1 billion, which results to 11,000 crores in Indian rupees. And whose money is this? This is people's money. And people end up getting logged out of their own account when something like this happens. So you can't go to the bank and ask for your money because, well, they don't have your money. They have lost it. So how do we fix this? Well, can we keep everything in physical cash? Well, this is definitely not possible because cash is really bulky. And we Indians have got a first-hand look of what happens when cash gets demonetized. You get up tomorrow morning and, well, your notes have zero value. So what do we do? Well, it turns out it's pretty simple. And it can be done in two steps. The first is that you don't let the digital ledger be controlled by a single entity. So in the case of banks, it's just the bank servers controlling the ledger and all the transactions going into it, right? So we don't let a single entity like a bank control the ledger. And the second step is we only allow the owner of the money to move it. Today, like I've just explained with banks, the banks can move your money further into all kinds of investments. So that is not something that we want in this new system of money. So now just a heads up, I will be explaining both the steps, but I'll start with step one, but there is no clear slide when I switch from step one to step two because both of them are interconnected and this is just like a single flow. So let's get into it. So for the first step, where we don't let a single entity control the ledger, well, what do? We distribute the ledger across multiple nodes. Now, this is a network. This is also called a P2P or a peer-to-peer network. Now, the speciality of this network is that anyone, you, me, anyone can join this network. We basically just download a software which runs the node of the network, and we become a part of it. And then we can have our own copy of the ledger. We can process the transactions. We can insert the transactions into the ledger. And this is the beauty of this public peer-to-peer network. And another thing to note is that on this network, you are pseudonymous. Basically, in the banking world, the banks give you an identity. But since this is a public network, your identity is somewhere between completely anonymous and having some basic items like an address, which we will get to later on. So for now, just think of this network like a black box. And you can think of it like a bank also. And we are sending the transactions into this black box for confirmation. So when we are making a digital transaction, what exactly are we doing? We are sending the transaction object to the bank's servers, right? It's happening behind the scenes when you're using internet banking. So in a similar way, think of this like a black box. And we have a transaction by Alice where she's sending $10 to Bob going into this black box. And for the next few slides, our main focus would be to understand how this transaction is crafted, this transaction object. How does it look like in the digital world? So before I go ahead, Brian, are there any questions that I may have to answer?
So if you guys have any question, please leave it down in the
Mhm.
in the comment section. In the comment section. I don't see any questions, so I think you can move on.
Awesome. So now the big thing about bank transactions is that they require you to have an identity. Okay. So let's say you go to the bank, you open an account. Then in this case, the banks give you a public identity, which is your account number. Now, this is called a public identity because ideally you can make it public. You give it to someone if you want to receive money into it, right? And apart from the public identity which the bank provides you, you also have your private identity, which can either be a combination of your email and password, or maybe your phone number and OTP. Now, this is called private because obviously you can't give your password and your OTP to someone. You must keep it to yourselves. And this is the private identity is what you use to finally move money that you have in the bank, right? But the main point here is that the banks are giving you the identity. And this is just an abstraction because eventually the bank can still move your money. So your identity is just some sort of uh, a middle layer that the bank tends to create. So what do you do in a world which is bankless? Who gives you an identity in a bankless world? And this is one problem that we will be discussing in this slide. Now, right now, this looks pretty scary, but I assure you at the end of this slide, you will have a better idea of what's going on here. So just like in the banking world, in the bankless world, or which you will eventually know, the blockchain world, you also have a private identity and a public identity. So how do you get the private identity? Well, your private identity in the bankless world is also called a private key. Now, this private key is nothing but a 256-bit number. And 256-bit number means there are 256 combinations of zeros and ones. If you do the math, this resolves to 10 to the power of 77 combinations. And we generate this private key randomly. So what this means is you're generating a random number between 0 and 10 to the power of 77. So this is a huge range. Now you might ask, why do we need such a huge range? Well, we need such a huge range because we must need some kind of an assurance that if I generate a random number and you generate a random number, there is no chance on earth that both of the numbers end up being same. Because if it's such a huge range, the a very good assumption is two numbers randomly generated in this range would never collide or be the same. So 256-bit, it's like a lot of bits, and we definitely can't represent it in zeros and ones. And not even in decimals, it would be quite a long number. So what do we do is we usually represent it in hexadecimal encoding. So here you can see this is hexadecimal number, which has 0 to 9 as digits, and then A, B, C, D, E, and F in the character set. And eventually it resolves to 64 characters. And this gives you your private identity. This is just like your password. You should definitely not share your private key with anyone ever. So now this is your private identity. How do you get the public identity? Well, the most beautiful part about blockchains is that your public identity is actually derived from your private identity. What's basically done is that we take your private key, which is a number, and we pass it into this function, which is called, used with the fancy name, elliptic curve multiplication. Now, I have pasted some reading material which will explain all the math behind this, but the main thing to understand is that it's a function that takes in a number and it gives another number, which is the public key. And this is a one-way function. So basically the inverse of this function doesn't exist. Once you get a public key, you can't go back and get the private key from this function. Now, the public key that you get is even larger than the private key. It's 512-bit. And ideally, if it's double the size in bits in hexadecimal, also you have double the number of characters, which is 128 characters. Now, this is in an ideal world, you can use this as your private identity, but the problem is it's huge. 128 characters is not ideal, considering your bank accounts just go up to 10 or 15 characters at max, right? So what do we do? Well, we take it through another layer of functions, and this time it's a hashing function and a combination of encoding. Now, these are fancy words, but what it really means is that we first pass it through a set of functions, just like the elliptic of multiplication. You get So public key is a number. We pass it through a function, and we get another number, which is the wallet address. And through the wallet address, you can't get back your public key. And this wallet address that you get, this is your public identity. And basically the encoding which we are using, encoding is just like hexadecimal encoding. On Tezos, we use base 58 encoding. So in base 58, apart from the digits, you also get a ton of other letters from the alphabet. So you can see here we have E, U, Z, F, P, all sorts of characters. And this eventually boils down to just 36 characters. And you can share this with anyone if you want to receive money in Tez. Obviously, Tez is the currency that is used on Tezos. So that was quite a mouthful, but long story short, we have a private identity that is randomly generated, and through that we generate a public identity by passing this number through a bunch of functions. Any questions up there, Brian?
Yes. So
Okay.
so there is a question.
Mhm.
I believe it's from Aaron. How can we trust these individual users within the network? Why give them access to a certain portion of the ledger, and can they tamper with it? Yeah, I have put it.
Surely, okay, yeah, we will actually get to it, and they can definitely tamper with it, but that's the beauty of it. So we expect that majority of the users don't tamper. So that's why we have this concept of 51% attack. If the majority of the users are not tampering with the ledger, then we are good to go. Because if someone tampers with the ledger and sends out a fraudulent transaction, the majority of the nodes will just reject it, and we are good to go. So I hope that makes it clear, but we'll get to it eventually. So just sit tight. Is there anything else?
Yeah. So I don't think there's anything else. I think most of it is about about the 51% attacks.
Okay.
So yeah, I
Yeah.
think you can move on. Yeah.
Awesome. So now the question is, well, you have your private identity and your public identity. Now, how do you use your identity to move the money? Well, to understand that, let's circle bank to banks again. In bank, we have the banker's check. Now, whenever we are giving a check to someone, we have four really important fields on the check. The first field is the to, and by to, it's to whom we are paying the money. Amount is obviously the amount of money. And then we have a from, which is your public identity, and it would be your account number. And then the most important part of the bank is your signature, of the banker's check is your signature. Now, what exactly is your signature providing here? It's providing a proof of your public identity. It's a proof that you are actually initiating this transaction, because it is an assumption in an ideal world that no one else can forge your signature. So your signature just belongs to you. And it's a perfect proof that you are the only one who can initiate this transaction through this check. So your signature is the proof of your identity. So in a similar way, in the digital world of blockchain, we have digital signatures. Now, ECDSA is the full form is elliptic curve digital signature algorithm. That's a lot of words, but I'll just explain what's inside it, and this will clear it out. So the first thing is the transaction data. Now think of the transaction like JSON or a JavaScript object. In a JavaScript object, we basically have fields. So here we have the three basic fields, which you also find on a check. We have the to. Now in this case, it will be the address, right? The address of the person we are sending the money to. From will be you, your address, and the amount. Now this amount will obviously be in the currency of the blockchain itself. So if you're on Tezos, it's going to be Tez. If you're on Bitcoin, it's going to be BTC. If on Ethereum, it's going to be ETH. So basically, this is the transaction data. And this transaction data can be represented in hexadecimal bytes. Even in JavaScript, you're going to see that there are all these functions that can take a JavaScript object and convert it to a sequence of bytes. And this is nothing but a number, a hexadecimal number. So now the ECDSA package provides a signing function. Now, what does the signing function do? The signing function takes in two numbers. It takes the first number is the transaction data, and the second number is your private key. Now, it takes both of these numbers and it gives you the digital signature, which is, well, it's another hexadecimal number. Now, the main thing to understand here is that your digital signature is derived from your private key. So if I use my private key, I'm going to get some other digital signature here. If you use your private key with the same data, you will get some other digital signature here. So this digital signature is dependent completely on your private key. So how do we actually verify whether the digital signature is actually authentic or not? Because in the case of banks, well, these days we have softwares that check whether the signature is actually matching the signature that we presented in the documents when we were opening an account. But how does that work in the digital world? Well, in the digital world, we use another function provided by the ECDSA package, and that's called the verify function. So one thing to understand here is that your private key gives you your public address, which we just spoke about a couple of slides back. And your private key also gives you your digital signature. So in some way, we can say that the address, your public address, and the digital signature must have some link, since the base is the private key in both the cases, right? So the verify function, what it does is it takes the public address and it takes the digital signature, and it gives a true output if the private key which generated this public address was the one that actually created this digital signature. So in this case, you see my from account is TZ1FXR, and that gave me this digital signature. And when I'm putting that and the digital signature here, I'm getting a true value. But the moment I'm putting some other public address, I end up getting a false value. So the signature, just like on a banker's check, it's a proof that the from entity has actually initiated the transaction. So just like in 51% attack, which we were talking about, the main thing that often is forged is the signature itself. So you send in a faulty transaction which has a bad signature. So let's say I am initiating a transfer from your account to someone else's account, but I don't have a control over your account. So I just forge a signature, which eventually gives a false output in one of the nodes, and the transaction never goes through. So this is the most beautiful part about digital signatures. Any questions, Brian?
Nope, I don't see any.
Okay,
Yeah, I think you
awesome,
can move.
awesome, awesome. So now we have the signature. Now, what do we do with it? Well, the signature is actually added to the transaction object, and it is sent into the black box for confirmation. So just like I said, think of this like a check that you are giving to the bank. In the check, you have the true and the from and the amount. And finally, you give a signature, which is the proof that, yes, I am the one initiating this transaction. And you hand it over to the bank, and then they process it and they confirm it. So that's how the whole process of transaction works from the outside world. So I'll give you a quick demo of how it looks like. So here I've got Temple Wallet, which is a Tezos wallet. Now just think of it like a wallet which you use, maybe PayPal or Venmo, or in India we have GPay and Paytm. So in here I have an account which I've called Alice, and here I have 65 Tez. Tez is the official token of Tezos blockchain. Now, just a heads up that I will be explaining more about Tezos in the next presentation, because that is where I teach you how to write smart contracts on Tezos. So before that, I will give a complete primer on how Tezos works. But today it's just going to be about blockchains. So yeah, back to this. I have an account where I have 65 Tez, and this is the public address of my account, or the wallet address. And here I have another account which I have given the alias Bob. This is the public address, and I have 20 Tez. So let's say I want to send $10 or 10 Tez to Bob. Then I click on send, and I choose a recipient, from my own wallet. Now, ideally, you can just add any valid Tezos address. Just for the sake of this demo, I'm choosing an address from my own wallet. For amount, let's say I select 5 Tez, and I click on send. And then I confirm the transaction. Now, in this process, what's really happening behind the scenes is that a transaction object is being created and it's being pushed into that black box we have been talking about all this while. So now it's been pushed into the black box and we're just waiting for a few seconds for confirmation. And in just a few seconds, you will see we will have 5 Tez less. Yeah, there you go. And now Bob has 25 Tez. That was pretty fast. So from a top level view, it just works like PayPal, Paytm, GPay, but internally, this is how it works. You have a transaction object and you push it to the network. So proceeding further, now I have been talking for the past 25-30 minutes, and you must be wondering, well, where is the blockchains? Where are the blocks? Like, where is the chain? Till now, I haven't really properly mentioned the word blockchain. Well, to understand about where is the blockchain, we need to go inside the box, inside the black box. So in here, whenever we are sending the transaction to inside the black box, we are not sending it to all the nodes together. Rather, we are getting connected to one of the nodes in this entire network, and we are sending the transaction to that node. So in here, in my wallet, you can see I'm connected to the Jakarta testnet node, and I'm only sending the transaction to this node initially. So every node has this memory called memory pool. You can think of this like a RAM where all the pending transactions are stored. So when I send my transaction to a node, it first goes into this memory pool. Now this memory pool is actually a part of the node. It's inside the node. I've just made it outside for clarity, but it's a part of the node's memory itself. So I send the transaction object, it goes to the memory pool, and then something happens. And this something is called peer-to-peer flooding. So the moment one node receives my transaction object, it floods the entire network with that object. So if one node receives it, every other node will be receiving it too. So just like you can see here, I sent it to this node, and this node has forwarded it to all other nodes. So now, since all the nodes have a transaction, one really important question comes up. Who processes and confirms the transaction? Well, from a top level view, it's the entire network that collectively tries to reach consensus on the transactions and the state of the ledger at regular intervals. And when I say collectively, it obviously doesn't happen that all the nodes are, all the nodes are doing it at the same time, but rather there's a proper process of consensus. Consensus also means coming to agreement. And this process is a part of something called the consensus protocol. Now, the consensus protocols come in different flavors and types, but most of them have a common sequence of actions or steps, and that is what I'll be telling you now. So the first step is always the same. We need to select a leader. A leader is selected at nearly regular intervals. And what does this leader do? The leader takes a set of pending transactions from the memory pool and processes them. Now, processing basically means you check whether it has a valid signature, and whether, let's say, if I'm sending someone 10 Tez, then whether my account actually has 10 Tez. Because if I have 5 Tez, then obviously that's an invalid transaction, right? So it takes all these pending transactions, it processes them, and it makes a block out of them. It basically collects all these processed transactions and puts them in a set called a block. And this is where the concept of blocks come in. Now, after creating the block, the leader sends the block out on the network. So just like a transaction is flooded to the network, in a similar way, the block, which we will eventually learn is also like an object, is flooded out on the network. And then finally, all the nodes that get the block have just one purpose. They can either accept or reject the block. Now, ideally, most of the blocks get accepted, but in a situation where, let's say, a block has a fraudulent transaction, once again, back to the question of 51% attack. If someone tampers with a transaction and sends it to me, and it is basically a bad block, then I just reject it. So depending upon the correctness, I accept or I remove it from my node. So this is the very standard steps that a consensus protocol follows. So now the main question is, how is the leader selected? Well, right now there are two very popular mechanisms for selecting leader: the proof of work mechanism and the proof of stake mechanism. Now, the proof of work mechanism is the more original mechanism that it was initially proposed as a part of Bitcoin and then was also taken up by Ethereum and several other cryptocurrencies. So, what really happens in the proof of work mechanism? Well, in proof of work, the network publishes a cryptographic puzzle. Now, this cryptographic puzzle is basically a really hard to solve mathematical problem. And I won't go into the mathematics, obviously, it's out of the scope of this session, but I have pasted links in the reading material where you can understand what the math is all about. So the network publishes this puzzle, and the nodes compete to solve this puzzle. And whichever node solves this puzzle first ends up creating the block. It's pretty fair and simple. And if you have heard of this term called mining, then the mining is nothing more than just this process of solving a puzzle and then ending up creating a block because you are selected as the leader. So this is proof of work. And in a similar way, we have proof of stake. Right now, most of the blockchains that are coming up have some form of modified proof of stake mechanism, including Tezos. So what happens in proof of stake? Well, proof of stake removes the whole concept of the competition of nodes. Basically, if you want to participate in proof of stake, then you have to stake the network tokens. So in the case of Tezos, you have to stake Tez on the network. And what the network does is it algorithmically selects a leader based on some random procedure. And this randomly selected leader then goes on to create a block. Now, why, you might ask, like, why do we need this stake? The main reason we need this stake is that on most systems, the stake is actually seized if a bad block is created. And also, stake prevents a lot of spam nodes from joining the network because you actually need to have skin in the game to join it, and everyone can't afford to stake the tokens and join the network. Now, you might have heard of all this controversy that proof of stake is much better for the environment than proof of work. The main reason is this, that you don't have to solve a puzzle, and solving this puzzle requires a lot of electricity to be spent, right? Because of all the work that the processor does in a node. But in the case of proof of stake, the automated selection of leader just cuts out all the electricity usage, and we get a much cleaner leader selection mechanism. So yeah, that's with the leader selection. Any questions out there, Brian? Because this was quite a lot.
Yeah, so I think a few questions here. So Parish has said, if all code is open source, why isn't it possible for someone to mimic a miner and send crypto from one wallet to another?
Yeah, like that is what the intention is. Like ideally, everyone can become a miner and do that. And but I don't really see the problem here. Like, yeah, if I do that, I have to send the transaction onto the network, and all the nodes have to accept it, right? It's not just me doing it on my computer. When I do it, I have to send it out to the world so that everyone knows that, yeah, this is the transaction that happened, right?
Yeah, okay. So there's another question. So a question would say that the proof of work and proof of stake follow the same private key checking method. Yeah.
That's the question. Like, do they follow the same private key checking?
Yeah.
Well, like it's nothing to do with the private key checking. Well, eventually the verification that we are talking about here, where is it? Right, this verification is the same whether you are on proof of work or proof of stake. This verification model is the same in all the cases. This is just for the first step. So this first step where you select a leader, in for that you have two different mechanisms: proof of work and proof of stake. After that, the transaction verification and everything else is just the same for both.
Okay. Yeah. Okay. I think we can go with one more question, and then
Yeah.
I think we can continue on. So, as Aaron has said, a leader is one of the users of blockchain. So, he's asking, so the knowledge of all aspects and components of a blockchain are compulsory to use it. How will the public gain access to this
Could you repeat, please? I didn't
method
get it.
of payment? Yeah.
Could you repeat once?
Okay, so Heron has said a leader is one of the users in the blockchain. So he's
Yeah.
asking that so would the knowledge of all aspects and components of a blockchain be compulsory to use it in some sense? And then he also asks how will the public gain access to this method of payment?
I didn't quite get the answer, like the question,
So
but the
yeah.
leader is basically a node. It's not just a, so I can, if I want to be a leader, I have to first run a node. Now this node, but when I say I want to run a node, I actually run the software provided by the the creators of the blockchain. So in the case of Tezos, we have this software called Octez, OCTEZ. You can Google it up. And when you run this software, everything happens behind the scenes automatically. It's not like I have to know the rules of the blockchain in order to be a leader. I just literally insert the command they ask me to, and the node is up and running. I'm not sure if that answers your question.
Okay, I think we can move on. I think that's the last of the questions here that I can see that is relevant. Yeah, you can
Awesome.
move from your slides. Thank you.
So yeah, now some examples of both of the chains using both kinds of mechanisms. For proof of work, it's all the OG chains like Bitcoin and Ethereum and also Dogecoin. And for proof of stake, we have Tezos, our very own chain. And upcoming ETH 2.0, whenever it launches, will actually be using proof of stake. So Ethereum will move away from proof of work and bring in the proof of stake consensus model. So yeah, that's all with the examples. So now we have to check how the block actually looks like. Like we previously we saw how the transaction looks like digitally. Now we have to see how the block looks like. Well, the block is also can be visualized like a JS object with different fields. Now these fields, the aliases that I've given are pretty random. It really depends on the blockchain what kind of alias they end up giving. But on most of the blockchains, these are some of the common aliases that you can find. So first we have the block number, which is basically just a sequence of numbers. So let's say if the current block is 2342, then the previous block must have been 2341. So just a continuously increasing sequence. Then we have the block hash. Now the block hash is the most important field of all, because what the block hash does is that it uniquely represents every block, apart from the block number, which is obviously a unique representation in itself. But how is the block hash created? So basically, we take in every field apart from block hash itself, and we pass these fields through a hashing function. And then eventually the number that we get, that is the block hash. So the block hash is an identifier for all the fields in one set. That's how we can think of it like. And next we have the previous block hash. Now this is a very important field too. This is the hash of the previous block. So every block will have the hash of the previous block. Now this can actually give you the hint of the chain, which we will get to. So if every block has the previous block hash and the previous block hash is used to create the current block hash, because that is also passed in the hashing function, then we are getting a continuous chain where every block is interconnected to the previous block. Then we have the block creator, which is just like the address of the node that created the block. Then we have the nonce. Now, nonce is actually specific to proof of work chains, because nonce is the solution to the puzzle, that the mathematical puzzle that I was talking about initially. And you can actually read through the POW material that I've pasted in the reading material links. That will be really useful. Then the timestamp. This is the timestamp at which the block was actually created by the leader. And then it has some bunch of other fields which we will get to. But the last important field is the transactions. And this is obviously, we must have transactions in a block. So how are the transactions actually filled up in a block? So the leader node basically takes the pending transactions from its memory pool. It verifies the signatures and checks if the transaction is actually valid. and inserts the transaction into the block. So one thing to note here is that the memory pool has like a whole lot of transactions, but the block size is limited. So on Bitcoin, we have a block size of 1 MB. So let's say if all the transactions are inserted and the block size is being more than 1 MB, then the leader must take out some transactions and keep the size of the block that it publishes on the network below 1 MB. So the number of transactions in a block is limited by block size. And all the transactions that didn't go into this block will eventually go on to some other block later on. So this is something really important and must be noted. So how often are blocks actually created? This is a really important question, because right now I've told you that each block has a number, but how often does this number actually increase? How often does the block appear on a node? So turns out it's different for both proof of work and proof of stake networks. For proof of work networks, the block time depends on the time that the node takes to solve the cryptographic puzzle, right? So if the puzzle is really difficult, the node will take more time to solve it. And if the puzzle is less difficult, the node can solve it in a faster time, right? So on Bitcoin, it's 10 minutes to solve the puzzle. So every block occurs once in 10 minutes. And on Ethereum, it's just 15 seconds. So long story short, on proof of work, block time is actually related to the difficulty of solving the puzzle. More difficult the puzzle, the longer the block time. And on proof of stake network, it's completely different, because on proof of stake networks, you already know there's no competition going on. We already know who's going to be the leader and who's going to create the blocks. So ideally, just to ensure, because there is some network latency, let's say if the block time is just 1 second, okay, but there can be some network latency if some block is going from USA to Australia, right? It might take more than 1 second for the block to actually travel through the internet, right? So in this case, some ideal block time is selected, and there must be that level of delay between two consecutive blocks. And on Tezos, that delay is 30 seconds. There are other networks where the delay is really less, like you even have networks with 1 second delays, but then they also have other procedures to ensure that the latency is never a problem when we are creating the blocks on the network. So yeah, that's about how blocks are created. Next comes the chain. So you already got a hang of what the chain will look like, because every block has a connection to the previous block through the previous block hash field, right? So why do we actually need the chain? Like, why can't the blocks just exist independently? Well, we need the chain for immutability. So let's say a new node has joined the network, and they want to download the entire ledger onto their chain. Now, what if when they're downloading the ledger, they end up getting a faulty ledger? How will they verify whether this ledger and all the transactions within the ledger actually happened and were actually initiated by the right accounts? In this case, the chain is really useful, because in the first case, it's all good, and that's why all the blocks are green. In the second case, the third block has a transaction that is manipulated, or it's a fraudulent transaction. Then in this case, what happens is that if the transaction is manipulated, the block hash of this node changes, because the block hash considers all the transactions when the block hash is being created or being found out by the hashing function. So if the block hash is messed up, then the link basically breaks, because the previous block hash is no longer valid. And this is basically a trickling effect. So every block hereforth from the manipulated block gets invalidated. And this is a really beautiful concept. And this is one of the parts of preventing fraudulent blocks from coming onto the network. So once again, back to the 51% attack thing. If a transaction in an existing block is manipulated and the chain is put out there on the network, then basically the whole chain starting from the manipulated block will be invalidated. So long story short, the chain provides immutability and ease of verification for the network nodes. So this is a really good website where you can get a proper understanding of how immutability actually works. So in here you can see we have, this is basically a simulation of a chain. We have 5 blocks in total, and all of these blocks are green right now because everything is good. Now let's say I go to the second block and I change the nonce, and you see the first block is still valid, but all the other blocks get invalidated. Now if I fix it back, well, we are good to go again. If I change the nonce of this block, the last 2 blocks get invalidated. Because the main reason is that, you see, the moment I change the nonce, the hash changes. Right? If the hash changes, the previous hash must change. Then this hash will also change. And it's a trickling effect once again, and everything gets invalidated from this block. So you can also try this out. The website is this, it's placed on the slides. And one thing which I missed, so the first block is actually called the Genesis block, and this block doesn't have a previous block hash because this is the first block that was created in the blockchain. So this doesn't have a previous block hash. So before going further, any questions, Brian?
Yeah. So a question from on the comments: how does a layer two a L2 batch together transactions? There is one question, and the other one is this actually another one. Who actually creates these puzzles to be sent to the blocks?
Could you repeat the second question?
Yeah. So like the second question is who actually creates these puzzles that are sent to the blocks?
Okay, who creates the puzzles? Okay, so I'll
Yeah.
get to that. First question was, how are the transactions processed in
Batch.
L2?
Yeah, so
How are
how
the
does
oh yeah
the transactions for for a layer to actually batch
yeah
together transactions? Yeah.
yeah okay, so actually that's a part of smart contracts. I'll get to it eventually, but I'll give you a small overview of it. So in L2, basically when we have all the transactions, the main check is the signature check, and the check whether the uh, whether, let's say, if someone is transferring 20 Tez to someone, then the account actually has 20 Tez, right? These are some of the most important checks in purely transactional rollups. This is the most important check. So this batching, when you say batching, it's not like we are batching stuff together in a block. In this kind of batching, mostly all the transactions are just verified and collected together. It's just a collection, nothing else. And it's put onto the smart contract of the rollup. And this smart contract then verifies the signatures. And depending upon what kind of rollup it is, if it's a ZK rollup, then on the rollup contract itself, these signatures and the transaction authenticity is verified. And if it's an optimistic rollup, then the authenticity of these transactions are verified by the node of the rollup, or the sequencer. That's what we call it. And they verify the signatures, and then they push it onto the smart contracts. So yeah, I'll get to it when we go for smart contracts, but I'm not sure if that answers your question. It's not like the blocks which I was talking about. It's more like just a set of transactions. uh, yeah,
Yeah.
Brian.
Okay. So
Okay, what was the
there's
next question? Can you repeat it? Maybe I just
okay. So
forgot.
the next question will be who actually creates these puzzles
Yeah,
that
who
are
creates
actually
the
sent
puzzles?
to the blocks? Yeah.
Okay, so actually you will get to know more about that in the reading material, but I'll just explain it anyway. So let's say this is a block. Okay, and in this block we have a bunch of data, right? Now when this block is created, depending upon which blockchain we are using, we use some fields out of this block to actually create the puzzle. So let's say we have the block hash, we take the block hash, and we take the account of the next leader. Okay, now we don't yet know who the next leader is, but let's say we just take your account. If you are participating in the competition, we take your account, we take this block hash, and we pass it all through another hashing function, and we get another number, right? Basically, just say we pass some data through a hashing function and we get some numbers. Now, this puzzle is basically that you must find a nonce. You must find a nonce, and this nonce is basically a number. And when this nonce is taken along with some other bunch of data that you will be putting in the next block, and you hash it again, then the next number that you get is less than the previous number. I'm just speaking, it's really difficult to explain without a slide, but the puzzle is actually generated. uh, it's not one entity on the network generating the puzzle, but it's the previous node and all the data that the previous node released when it was creating the blocks, that is used to generate the puzzle. Because in this block there are a lot of data that is unpredictable, because you can't predict what the block hash will be for the next block, right? So these unpredictable numbers are used to create the puzzle. And I would really recommend going through and reading this proof of work consensus reading material. It's really elaborate, and you will properly get to understand what this whole concept of finding a number less than the previous number actually means.
Yeah, okay. I think there are no more questions. You can continue on.
Awesome. So now the next question would be, why would someone want to run a node on this network? Because running a node requires electricity, right? It doesn't matter whether it's a proof of work consensus model or a proof of stake consensus model. There will be some amount of electricity that I have to spend when I'm running a node, right? So why will I do it? Well, there are some incentive models attached to every blockchain. And usually we have two models. One is the transaction fee model, and one is the block reward model. In the transaction fee model, now both of them exist on a blockchain. It's not like we just have one of the two models. In the transaction fee model, we basically have a variable fee which the sender of the transaction attach to the transaction object. So let's say if I am sending a transaction, I attach a fee of 221. Now this can be any like it can be either Bitcoin or Tez or whichever blockchain I'm transacting on, and I attach a fee which will go to the leader that ends up creating my block. And the leader that creates the block also ends up getting a reward by the network itself. And this is what the network creates when the leader is creating the final block. So when we say we are mining crypto, we basically mean we are creating a block and the network is rewarding us with extra tokens. So in the transaction, it looks like this. And in the final block, we will actually have a block reward field, which will have a certain value depending upon what the value is on the network right now. And we have a total fees field, which basically is a field that sums up the fees across all the transactions added to the block. But yeah, the most important field here is the block reward, which depends on the blockchain, how much reward they are providing right now. So now you would ask, like, how can this compete with real world finance? Because on real world finance, we have so many concepts: options, futures, money market, foreign exchanges. How can this just a system of money compete with all this? Because all this requires mathematical logic, right? And right now, whatever you have learned, all this, there's no logic here, right? It's something coming out of the box. So for this, we have something called smart contracts. Now, smart contracts are not there on all blockchains. They are on selected blockchains like Ethereum and even on Tezos. So what exactly is a smart contract? A smart contract is a piece of code that can run on one of the nodes of this entire network. Now, these nodes are nothing but computers, right? So they will obviously have a processor which can run programs, right? So these programs are called smart contract. As you can see here, we have a node which has a contract code. And now every contract needs some kind of a compiler or an interpreter to actually execute itself, right? So every software of the node comes inbuilt with a code interpreter. So if you download Octez, which is the software for Tezos, Then you get the code interpreter, which is also called the Michelson interpreter. We'll get to it in tomorrow's session. But that comes inbuilt into the software, and that is where the smart contract code actually runs. So yeah, smart contract is a program or a code that is stored and executed on the nodes of the network. And one thing to note is that every contract has an address or an identity. So just like if you have an account on the blockchain, you have an address, a public address. In the same way, every contract has a public address using which users can interact with the contract or the code that is within the contract. So how does smart contract transactions look like? Well, in contracts, we have two kinds of transaction. One is the deployment transaction, where you actually deploy the smart contracts onto the network. And one is a contract function call, when you're calling a certain function of the smart contract. Now, in the deployment transaction, apart from the basic fields like from, amount, and fee, we don't have a to here because we are not really sending it to anyone. We are just putting it on the network. The code of the contract is attached to this transaction, and we just send it to the network. And after processing, all the nodes end up getting the code in them. And then we have the contract function call transaction. Now in here, the from would be your address, and this one you see an address starting with KT1 on Tezos. All contract addresses start with a KT1 attached to it. So this is the contract address. You are sending a transaction to the contract. And then the basic fields, amount and fee. Now this amount will actually go to the contract, and then the contract can do anything it wants with it. And then you mentioned the function that you want to call within the contract. So here I'm assuming that this contract has some function called process. It's just an assumption because all of these are like random values. And then we pass the parameters that the function takes. If it doesn't take any parameters, we just don't pass anything. But depending upon what parameters it takes, we pass in those in the parameters field.
Hi.
Yeah.
Hanchu, I think
Yeah.
I think you need to show your slide. I think it's still stuck at the same slide. You're still
Sorry?
stuck at the you are still stuck at the block slide. Yeah. So like the slide there, you're supposed to show is not showing up. Yeah.
Is it showing? Which slide is it showing right now?
Okay. Now it's showing the smart contract slide, which is slide 32. Yeah. Yeah. So now we are showing the smart contract transactions. Yeah.
So this slide was never shown before.
Yeah, this slide was not shown before. Yeah, so this is
And this was shown.
Okay, I think this should be new. Yeah. Yes.
So I can leave out this one out and go to this one, right?
Yeah, sure. Yeah.
Okay. So in smart contract transactions, so basically smart contract transactions are divided into two types. First, we have a smart contract deployment transaction, and then we have a smart contract function call transaction. So in the deployment transaction, it's where the contract is actually being deployed on to the network. So in this case, we do not have a to field because we are not sending this transaction to anyone. Rather, it's just a code being deployed to all the nodes in the network. So we just have a from field, an amount field, and a fee, and the code of the smart contract, which eventually gets to all the nodes onto the network. And then we have a function called transaction, where we are calling a specific function within the contracts. Now, tomorrow when we write the contracts, we'll get to know what these functions do, how they are structured. But for now, just understand the pattern of the transaction. So here we have a from field, which will be your address. The to field is the address of the contract. Now on Tezos, all contracts start with a KT1 alias. So basically, if it's a contract, then it starts with KT1. And then you send an amount. Now this amount will go to the contract, and then the contract can do anything with this amount. And then we have the standard fee. And this function is a function that will be within the contract. Now, right now, I'm just assuming that there is a process function because these are just random values I've placed. But if there is a process function in this contract, then that will be called with the parameters that I pass in the parameters fields. So this is like very intuitive. We are basically calling a contract which has some function, and we are passing in some parameters. and then the execution takes place in the nodes and we get some kind of result. So yeah, any questions, Brian? Because maybe I lost track, so I should answer the questions.
Yeah, sure. Okay, I have a question from Kumar. He
Mhm.
says that we can detect that someone has changed on the block by comparing the block hashes, but if the miner deploys a faulty block in the beginning itself, how can we detect the faulty block? Yeah.
You mean in the Genesis transaction? Well, in that case, like let's say we have this. If it's done in the Genesis block, well, even if it's deployed, we are good to go, because it's not the entire chain. This is the starting. You can't go wrong from the starting, because then this becomes the source of truth, right? If your source of truth can't be wrong. This is what it is, right? And we are building everything on top of that. But once you start building it and then something goes wrong, well, then you have to invalidate the entire chain from that block onwards. I think that should answer your question.
Okay, the next question would be that I get confused between the ledger, the leader,
Yeah.
and the block. Could you explain again?
The ledger, the leader, and the block. So see, the ledger is the blockchain itself. Okay. Ledger is basically a document that stores a bunch of transactions, and the blockchain stores a bunch of transactions, right? So that is the ledger. The ledger is a document that is on a node or on a computer, which is the leader node. And this leader creates the blocks. Now this block is also, we can also think of a block like a document, another document that carries all the transactions. So to wrap it up, the leader is a node that has a ledger or the blockchain within its storage, and they end up creating the block which gets attached to the ledger. Does that answer your question?
So there is this question.
Mhm.
The minor node and the leader node both refers to the same node, right?
The Maya.
Okay. I don't think we have any more questions. You can continue on. Yeah. Thank you.
Awesome. So the next thing is the gas system. So whenever we are running a contract, as we can see here, when we are calling a function, now these contracts, these are programs, right? And in programs, we have logic. And when we deal with logic, we have instructions, right? We can have the add instruction, multiply instruction, basically arithmetic instructions. And apart from that, we can have conditionals and several other form of instructions. Now, usually on smart contract systems, we have the concept of gas. So whenever some kind of an instruction is executed, so let's say we are adding 2 and 3, then we attach some kind of a gas consumption with this instruction. Now, gas is nothing more than a unit of computation. It doesn't have any, it's a scalar value, so it doesn't have a unit, but itself is a unit of computation. So for add instruction, let's say we have 20 gas being consumed. For multiply instruction, we have 25 gas being consumed. Okay. Now these are arbitrary values. If you want to see the actual values, you have to check out the code of Tezos or Ethereum, depending upon which system you want to check. But the main reason of having gas is that we have an upper limit on the number of or the amount of gas that can be spent. So on Tezos, for every operation or transaction, the maximum gas or the maximum amount of computations that amount to a certain gas limit must not be more than 1,040,000. So if you're, let's say, if you have a contract that keeps on doing computations and the added gas consumption goes above 1,040,000, then the transaction just fails. You can't go. It's going to give an error called a gas exhaustion error. And in a similar way, we have a gas limit per block. So for every block, we can just have at max all the gas consumed across all the transactions must be within 5,200,000. If it's above that, then you can't really form the block. So the thing to consider here is that on Bitcoin, we have a 1 MB block limit. It's a proper size. But in the case of Tezos and even on Ethereum, we don't have these, like kilobytes or megabytes. Instead, we have these gas units. And the gas units give us the upper limit for the amount of transactions we can keep in a block. So even a simple Tez transfer has a fixed gas attached to it. So if you are just transferring a simple Tez simply, transferring Tez simply, then you just pay 1450 in gas units. This is like a fixed cost for every transaction that you do, which is a simple Tez transfer. So yeah, that is the gas system. Now, how does it fit with the entire model? Well, just like I said, we replace the block size and also the fees with gas usage. So in the first case, you see here we have a transaction. It's got the basic fields, and then it's got 3 other fields. Once again, the aliases have been given by me. The aliases can differ from blockchain to blockchain, but it's usually these 3. So we have a gas reserved. Gas reserved basically means the maximum gas that can be spent by the computations on this transaction. Now, this gas reserved field can be anything, but it must be within the gas limit. So for the transaction, this must be less than 1,040,000. And then we have the gas used, which is the actual amount of gas which got used from the reserved gas. So if I reserve 25,000 gas units for this transaction and it used this much, then I'm good to go. And then we have the gas fee. Now, gas fee is the amount of fee that we pay for each unit of gas used. So when a leader actually puts this transaction within a block, the amount of fee that the leader gets is basically 4 multiplied by the gas used. So this is a better model of fees, because in this case, the fees depend on the amount of computations. Because when you are doing computations, you're basically spending electricity, right? The leader nodes need to use electricity to do all these computations. So based on how much computations they do, they get an equivalent amount of fees. And this is the best part about the gas system. Now, in this case, you see I've written a transaction. Its transaction has failed. The transaction has failed because the gas reserved for this operation was just 25,000, but for some reason it ended up taking 32,000 gas. Now, the gas limit is usually provided because, let's say you are interacting with a bad contract or a malicious contract whose only purpose is to just suck up all the gas that you provide to the system. Then in this case, it is ideal that you provide an upper limit. And the moment it crosses the upper limit, the transaction doesn't go through. And in this case, you eventually the blockchain is saved from spam transactions getting bottling up. And then this is how the gas fits in the transaction. As for the block, everything adds up, and we have 2 fields. We have the gas reserved, which is gas reserved across all the transactions, and this must be less than 5,200,000. And then we have gas used, which is gas used across all the transactions. So it's just a summing up of individual transactions. So now the final thing, let's explore some live transactions and blocks and smart contracts. Let me just open it. So yeah. Now every blockchain has a blockchain explorer. So on Tezos, we have this blockchain explorer called TZKT. If you go to Ethereum, we have on Ethereum EtherScan. Now on these explorers, you can basically explore the current state of the blockchain. So in here, you can see we can observe the blocks appearing on the system. So here we can see next block in 5, 4, 3, 2, 1. And sometimes the block is late for a few seconds. Yeah, there you go. We have a new block. Now, if we open up this block, here we can see, tomorrow I'll explain all these, like the concept of cycles. But right now we can see the block has a timestamp, that is the Unix timestamp at which the block was created. We have the payload proposer. Okay, that's not important. The block producer. So here we can see the Coinbase Baker, whose address is this, and this is the leader. This is the leader that produced the block. Finally, here we have the block reward. So the Coinbase baker ended up getting 10 tests for creating the block. And these are the two important fields, the gas reserved and the gas used. So here you can see 5,200,000 gas was reserved, but out of 5,200,000, this much gas was reserved and this much gas ended up being used. And this was the total fees collected across all the transactions. And in the middle panel, you can see all the individual transactions. So in the first case, this is a simple Tez transfer transaction. And here you can see, like I said, the gas used, it's close to 1,450. This one here is a contract call. So this is a contract which is given an alias, but here you can see this is the contract address. And in the transaction, the set entropy function in the contract was called. Now on Tezos, the functions are actually called entry points. So if you click on entry points, you can actually see the functions within the contract. And you can also see the code of the contract. Now on Tezos, we have this language called Michelson, which is the final language in which all the contracts are compiled. We'll get to this tomorrow, but today you can just take a look at how all of this fits together. And if you go to Ethereum, it's kind of similar. We have the blocks. If I click on a block, then we have the block height, which is the block number. We have the timestamp, the number of transactions, the mined by. Now, in this case, this is the leader. So this also answers the question. The leader is the miner. Then we have the block reward, which is going to the miner. Now, difficulty. Now, see, just like I said, there is a difficulty for the puzzle that is being published onto the network, and difficulty also has a numeric value. So yeah, this is the difficulty level of the current block. Finally, yeah, now you can see gas limit and gas used. Most of these are interrelated between Tezos and Ethereum. It's mostly what's going on behind the scenes that's different. So yeah, that's about it, I guess. Any questions?
Okay, I do have a question from the
You guys can ask questions from like any slide. Just go through the slides, and if you have any question, you can ask.
Yeah, please put your questions into the comments. If you have not posted that. And one question from the audience is that, so does the Tezos blockchain have the same gas concept as the Ethereum blockchain, or is there any differences in both of them?
So actually, there is the gas concept, as in the gas usage and everything is the same, but there is one difference which I can show you. And the one difference is that on Tezos, apart from, let's open a transaction. So let's say if I open this transaction, so in this transaction, you can see this is the gas reserved. This is the gas that was actually used. And we have some associated gas fee. But the main thing to look at is this, the baker fee, which is an additional fee that you can attach when you are sending a transaction. So on Ethereum, like right now on Ethereum, we had this thing called 1559 Ethereum improvement proposal, which changed some stuff. But on base Ethereum, we just had the concept of, so with every unit of gas, we'll have some gas fee. So apart from that, on Tezos, we have an extra fee that you can send to the baker. So if you want your transaction to be processed really, really fast by the baker, then you can attach an extra fee and give it to the baker. So this is one fundamental difference. This is something which is fundamentally different from Ethereum.
There is another question. So, Mr. Francisco say, I'm confused where is blockchain nodes data stored at.
Sorry?
So, where is the blockchain nodes data stored at?
Stop that or store? You mean?
Store. Yeah, store. I mean the store.
The blockchain, it's within the, like a node has a storage, right? So let's say if I'm running a node, I will have some SSD storage where all the data will be stored, right?
So there's another question. Does the Tezos blockchain also have the concept of anchor blocks?
Oh well, it's like we don't have it in that sense on Ethereum.
Okay. Is it always necessary? So another question from
Mhm.
Kumar. Is it always necessary to interact with a smart contract while doing a transaction?
No, it's not. So let's say if you're just sending a normal, if you're just sending test to someone. So let me check if there's some transaction. Um, okay, there isn't a simple test transfer. Okay, yeah, there is. So in this case, it's just a simple test transfer. So we are not interacting with any contract. It's just someone sending test to someone else. So in this case, yeah, we don't interact with the contract.
Okay, I think that's the last of the questions that I've seen. Yeah, so you can move on to the last part if I'm not wrong, or is this the last part? Yeah, this should be
This
the
was the
last.
last part. Yeah,
This is the last part. Okay,
yeah.
guys. So if you have any
If
more
you have more
questions,
questions, you can reach out to me on Discord.
and I have shared the links on into the comments as well. So if
Yeah.
you need to go to the Discord link or if you need to go to the GitHub link, I have also shared that in the comments as well. Which please use them. If there is nothing else, we can actually end it off here. So actually, the next workshop would actually be to tomorrow and on the 13th of July. So it's going to be for building a D app on Tezos in SmartPy, and yeah, it'd be the same time as today as well. And then yeah, if there is nothing else, I would like to thank Panchu for actually for actually presenting on what is blockchain and the money revolution in this. Yeah. Okay.
Thank
If
you.
you have any other comments or questions, please leave it down there in the comments, and yeah, we can answer it like in the either in the Discord, or you can actually ask Andrew on Discord as well. Yeah. Okay. Thank you, everybody. Yeah, and have a nice day. Yeah. Okay. Thank you.